Welcome to Summarize Science. Ever wondered if deep learning is more simple than it looks? This paper introduces a crazy idea that neural networks, even when trained to do completely different things, tend to operate within the same limited space. Think of it like this. Imagine a bunch of artists, each painting different subjects. Surprisingly, they all end up using similar palettes of just a few colors. This research shows that there is remarkable similarity in the networks. The researchers analyzed over 1,100 models, including large language models and vision transformers. They discovered that regardless of how the networks were initialized or what data they were trained on, they converged to shared spectral subspaces. These subspaces capture the majority of the variance in the network's parameters using only a few principal directions. Page 1 helps us visualize the Universal Subspace Hypothesis and the low-rank joint subspace of Witts. This finding has huge implications. It suggests that instead of needing tons of data and computing power to train new models, it could be possible to find and take advantage of these universal subspaces to achieve training with less resources. Page 2 further contextualizes that we're talking about parameter or weights level convergence, not the representation level, which would be easier to show due to data dependency. There are implications for transfer learning and weight sharing too. This is not only more efficient, but also better for the environment because it reduces the carbon footprint of large-scale AI. The existence of these universal subspaces could explain why models with way more parameters than training samples can still generalize well. The researchers showed that the fidelity of this universal subspace correlates with quantity and quality of the trained models, leading to the possibility of ideal, universal subspaces. Models with better data and optimization get closer to the ideal configuration. Page 3 explains some of the theoretical conditions and setups. The work also shows that the architecture of the model may be more important than things like the data it learns from or initialization of weights. These are some of the biggest ideas in the research paper. Our report wouldn't be complete if we didn't mention some limitations. There are limitations such as the interpretability of principal directions. To recap, deep neural networks, regardless of the tasks they are set up to do, learn very similar parameter subspaces. Discovering and leveraging these subspaces can mean training becomes much easier, more memory is saved, and there is more efficient and easier scaling and inference. This can be huge for under-resourced researchers, institutions, and communities. It allows everyone to build on these state-of-the-art models without insane computer infrastructure.